Hello, and thanks for joining us on this webinar titled What's New in Amazon EMR. My name is Radhika Ravirala. I am a data and analytics specialist at Amazon Web Services. For those of you who are just starting on the AWS platform, Amazon EMR is a managed Hadoop environment on AWS that allows you to quickly and cost-effectively process, analyze vast amounts of data. In today's session, we will dive into new enhancements into the Amazon EMR service. These include Spark performance improvements, support for record-level inserts and deletes to your data lake on Amazon S3 using Apache Hudi, cost optimizations with Spot provisioning, lake formation integration with EMR, security features, and we'll wrap up the session with some of the new additions to the Amazon EMR notebook capabilities. As you can imagine, data engineering platforms are evolving, but we do see a common pattern. There are lots of clients, such as your notebooks, your edge services, some level of orchestration that is happening through Apache Airflow, AWS Step Functions, and then completely managed clusters that are running all across your organizations. Now, compared to on-premises, most customers who run on the cloud choose a combination of two patterns. In this pattern, the data always resides in S3 instead of HDFS. And then customers run a combination of transient and persistent clusters. When customers ask about which pattern they should run, we tell them that it's a choice. And to give you an example, long-running clusters with auto-scaling enabled is great for lines of businesses clusters. What that means is if you have a large number of short-running jobs that you want to run at a regular frequency, by leveraging a long-running cluster, you can save costs for multi-tenanted data science and data engineering jobs. Similarly, transient and job scope clusters work well for long-running pipelines. It is ideal when you want to separate production pipelines into job scope clusters and reduce the blast radius. As the common architectural patterns for data platforms have evolved across notebooks, across the orchestration services, and across the managed clusters, we have made improvements across the board. So let's begin with the look at the Apache Spark improvements we have done on Amazon EMR. So Amazon EMR runtime for Apache Spark is a performance-optimized runtime for Apache Spark, which is available and turned on by default on the Amazon cluster. It's a runtime that is built on top of the optimized version of Apache Spark. It gives the best performance by running up to 2.6 times faster than Spark with EMR that is running without the runtime. It provides the best performance even when compared to the vanilla version of Apache Spark that you find in the open source community. To measure the improvements, we compared EMR 5.16 with open source version of Spark running 2.4 with EMR 5.28 that has the EMR runtime for Apache Spark and also compatible with Apache Spark version 2.4. In order to measure this, we used a TPC-DS benchmark queries with 3 terabyte scale and ran them on a 6-node C4 8 extra large EMR cluster with data in S3. When you add up the execution of 104 queries from TPC-DS, we observed a 2.6 faster performance of the Spark runtime versus EMR running Spark without runtime. When comparing these runtime versions with other third-party managed Spark offerings running their runtime technologies, we were able to get 1.6 times faster. This makes Spark on EMR this fastest Spark offering available, with the added benefit that it is 100% compliant with Apache Spark APS, which means that you can bring your existing Spark applications and run it on the latest EMR, and you will notice a significant improvement in the performance. Let's take a look at some of the benchmarking that we have done. So if you look at the runtime for 102 TPC-DS queries that were run against EMR 5.16 with Spark 2.4 and compare it against EMR 528 running the same Spark 2.4 version, you will notice that the difference is up to 2.5 times faster. Similarly, if you compare the geometric mean for the 104 TPC-DS queries, there is also a similar improvement in the performance. We also compared the running time of long-running queries. These are queries that run for 90 seconds and longer, and we observed a 5 times speed up on the long-running queries as well. When it comes to short-term queries that are running 90 seconds and lower, again, the speed up was up to 2 times more. So these performance improvements have been possible due to a lot of improvements that have been enabled on the Amazon EMR service. For example, the job startup times. By default, Amazon EMR uses Apache Spark's built-in dynamic executor allocator, which waits till all tasks are issued to begin creating new executors. As a result, number of executors can ramp up slowly, which may impact the short query performance. EMR service has gone ahead and implemented eager allocation of executors, which has significantly improved the short query performance, as you can see from the graph. The chart shows the correlation between performance improvements and the job runtime when eager allocation is turned on versus when it's not. Short-running queries see the maximum performance through eager worker allocation. Another feature that was introduced into the Spark runtime is the dynamic partition pruning. Dynamic partition pruning improves job performance by more accurately selecting the specific partitions within a table that need to be read and processed for a specific query. By reducing the amount of data read and processed, significant time is saved in job execution. Dynamic partition pruning allows the Spark engine to dynamically infer at runtime which partition need to be read and which can be safely eliminated. Yet another feature that was introduced into the Amazon EMR service is the data prefetch. By prefetching the data required for a query ahead of time, we were again able to see significant improvement in the benchmarking that we have done with the TPC-DS queries. So in summary, the optimizations for Spark applications running on EMR fall into a few categories. They include configuration changes that have to do with adjusting CPU to disk ratios, setting the driver and executor configuration, adjusting the heap to garbage collector ratio, modifying the instance defaults, so on and so forth. It also has to do with implementing a better planning and optimization through the use of dynamic partition pruning, flattening of subqueries, join reordering, etc. Query execution also improved due to data prefetching and other techniques that were introduced into the Amazon EMR runtime. Similarly, job startup times as well as eager executor allocation have helped drive the performance of Spark applications significantly on Amazon EMR. So to take advantage of these optimizations, it's just a matter of getting on to the latest version of EMR without having to make any code changes to your existing applications. The second new feature introduced into Amazon EMR is record level insert, update, and deletes that are made possible with Apache Hudi. So to think about this feature, let's go back to the architectural patterns for data lakes. So most data lakes have a common pattern. Data comes in from databases, application logs, event streams. You want to store them in S3 and run queries. However, in reality, S3 does not support native constructs such as a database does. A common workaround to that problem is to create raw tables and create derived tables suited for business needs. While this method has worked well, it can add a lot of overhead because you have to recompute all the data for a small change. For example, a small change in records or a late arriving data in your real-time ingestion streams, change in the schema, bad records, can all cause a recomputation of data from your raw tables into derived tables, adding significant latency to your processing time. The second problem is that as the data starts to get bigger, the ETL pipelines required to convert raw tables into derived tables take longer and even cost more. In addition, common use cases are still difficult to implement. For example, enforcing data privacy laws, such as the GDPR compliance, is very hard to implement with a data lake built on S3. And this is because deleting data within a specific time frame, deleting data across all data sets, and identifying files and partitions with the specific data that needs to be deleted is still tough due to lack of indexing on the data lake storage. So think of it as having a book and you want to republish the entire book just because you want to delete a single line in the book. Yet another use case that is hard to implement with the data lake on S3 is the change data capture. As bulk loads do not scale, there is no support for upserts on S3. Data quality is a serious concern, and you typically cannot give the similar guarantees as a database with your data residing in S3. Another use case where insert, delete, and update are significant is the streaming data ingestion. This is high volume, time ordered data where you want to eliminate duplicates as they mess up with your analytics. However, there is no fast way to ingest that data into Amazon S3. On top of it, schema management and checkpointing make it really hard to apply changes from a streaming source into your S3, extremely difficult. So this is where Apache Hudi helps. Apache Hudi is an open source data management framework used to simplify incremental data processing and data pipeline development by providing record level insert, update, upsert, and delete capabilities. When you write your data set in a Hudi format, Apache Hudi stores and indexes your data that can be read through querying engines such as Hive, Presto, and Spark SQL. Hudi is important because Hudi enables near real-time ingestion of data, which means that your batch jobs run much faster. It gives you a unified, optimized analytic storage so that row-level deletions can be simplified for enforcing data privacy laws. It, in essence, forms the building block for building great data lakes. On top of it, it's all open source and supports all open formats. In technical terms, Apache Hudi supports a few primitives. Those include the support for upsert with fast pluggable indexing, atomically publishing your data with the rollback capability and save points, achieving the snapshot isolation between your data writers and the queries that are issued against the data, as well as being able to control file sizes to keep your query performance excellent, as small files can hurt query performance considerably. It also allows you to asynchronously compact your columnar as well as row formatted data, giving you the ability to consume changes incrementally as opposed to wasteful scans. In addition, it also provides you with a timeline metadata to track the lineage of that data. Hudi provides a couple of storage type abstractions to help work with the data. The Hudi storage types define how the data is laid out on the distributed file system and how the primitives we spoke about, namely the upsert operations and the delete operations, as well as the timeline activities, are implemented on top of such organization. That is how the data is written. In turn, it also provides you with the concept of views that define how the underlying data is exposed to the queries. That is how the data is read. Now, on the storage types, Hudi provides two abstractions, copy on write and merge on read. For the copy on write, Hudi stores the data exclusively using columnar file formats, for example, Parquet. When updates are applied to a copy on write table, it simply versions and rewrites the file by performing a synchronous merge during the write. Now, when it comes to merge on read, the data is stored using a combination of columnar format, Parquet, and row-based Avro format. When updates occur to a merge on read table, these are logged to Delta files and later compacted to produce new versions of columnar files. In addition to the storage types, Hudi also exposes 3 different types of views: a read-optimized view, an incremental view, and a real-time view. In a read-optimized view, queries see the latest snapshot of the data as of a given commit time. In incremental view, queries will only see the newly written data to the dataset since a given commit or a compaction time. When it comes to the real-time views, queries on this view see the latest snapshot of the dataset as of a given delta commit action. Now, to get a better understanding of how all this works, let's take an example. So we begin with a copy on write example. And in this example, we have inserted 5 different records, A, B, C, and D, that are neatly packed into 3 different files. So at commit time 0, a read-optimized view on the copy on write table provides you with the latest from all the 3 files, which is A, B, C, D, and E. And an incremental view at this time also gives you the latest copy of the data, as this is the first insert that you're performing into this storage type. Let's contrast that with the merge on read storage type. As discussed earlier, merge on read storage type exposes 3 different types of views. So read optimized, incremental, and real time. So if we run through the same example as before, where we initially insert 5 records which go into 3 different files, and at this time, if you query any of the 3 views, they all essentially give you the same results, which is the initial set of initial set of records that you have. Now, after a certain period of time, updates have occurred. D has changed to D prime and A has changed to A prime. And these updates neatly go into log files called delta files. And as you can see, they are placed in log file 0 and log file 1. At this time, which is delta commit time 1, if you query the views, for the real-time view, you get the most up-to-date information, which is A prime, B, C, D prime, and E. For the incremental part, you only get the data that has changed, which is D prime and A prime, and the read optimized essentially remains same as your first insert. And after some more time, you have additional updates that came in where E changed to E prime, A prime changed to A double prime, and you inserted a record called F. And as you can imagine, these additional updates go into the log files again, the delta files. And if you query the data at this time, the real-time view query gives you the most up-to-date information. Incremental gives what has changed since the delta commit time 1. And as you can see, the read optimized remains the same as your initial insert. Now, let's say as a last step, you have performed a compaction of all your changes into your base files. And now, after the compaction, if you run the queries, your real-time view will give you the most up-to-date information. And as you can see, your log files are merged with your base files, and the read-optimized view also gives you the latest snapshot of the data at that time. Now, merge on read is ideal when you want to ingest data available for query as fast as possible, and your workload has sudden spikes or changes in pattern. As an example, think of bulk updates to older transactions in your upstream databases that can cause updates to older partitions in S3. So this is an ideal scenario to use merge on read. So why should you use Apache Hudi? So the reason for that is with Apache Hudi and Amazon EMR, you no longer need to build custom solutions to perform record level insert, update, and delete operations. Using a Hudi, you can create data sets that are optimized for either read-heavy or write-heavy use cases, and Hudi will manage the underlying data stored on S3 using open storage formats. It'll allow you to comply with data privacy laws, consume real-time streams, and change data captures that are coming in from your databases, have the ability to reinstate late arriving data for your real-time ingestion, and be able to track change history and apply rollbacks as necessary. So let's run through a quick demo of how Apache Hudi works with Amazon EMR. In this demo, we'll ingest data into Amazon S3 and write it as a Hudi dataset using Apache Hudi running on the EMR cluster. And once the data is written in a Hudi format, that data is available to be queried using either the Presto, Hive, or Spark SQL analytic engines. We will also show how to apply upserts and deletes on the same data and ensure that when we query the Hudi dataset after the upserts are applied, you see the latest data. So let's dive into that example using an EMR notebook. All right, jumping into our Amazon EMR notebooks, we start with the basics where we load the necessary Spark packages as indicated here, and then we start the Spark application. Next, we do some necessary imports to be able to use the Apache Hudi APIs. And more specifically, in this section, we are specifying the input dataset bucket where we will be reading the data from. And for the purpose of this demo, we are using Amazon Product Review as our dataset. And we also specify the output bucket where the Hudi dataset will be returned to. Now that we have that, we read the input data source into a Spark data frame. And we sample a few records just to see how the data is laid out. And as you can see, since this is a product review database, we have a review ID, a customer ID, a product title, the rating for that particular product, and the date that the product was reviewed on. And once the data is sampled, we are ready to begin writing in a Hudi format. Now, before we can write in a Hudi format, we need to specify a few options. The first one being the storage format that we will be using. In this case, we are using the copy on write storage strategy. As you may remember from the presentation, there are two modes, copy on write and merge on read. In this demo, we'll be using copy on read. Hudi also expects some other options, such as the primary key or the record key that it should use when writing the dataset. And in this case, it's the review ID. It also uses another key called precombined key. Now, if two records have the same key, precombined key will be used to determine which record to pick. And in most cases, it should be the latest record, and that is determined by the timestamp in your data set. Hudi also enables you to specify whether you want to sync your metadata with Hive, and that can be enabled by using the sync enabled opt key option. You can also specify how you want to partition your data, which in this case is going to be year, month, and day. With those options all specified, we are now ready to write our input data set to Hudi. As you can see here, we are using the write API and we are using the format as arc.apache.hudi. You also might notice that we also need to specify an operation key that tells Hudi whether this is an insert, upsert, or a bulk operation. In this case, we are writing the Hudi dataset as a bulk insert. Once the dataset is written in a Hudi format, you can navigate to your S3 bucket location where the Hudi dataset is written and notice that it creates a bunch of directories for writing your data. And most prominently, you'll observe that the data files go into the partition structure which you have defined, which is year, month, and day. And as you navigate, you will find that you will find your year, month, and day specified. And you will also notice that at the very beginning, there is a .hudi file folder that gets created. Now, this file folder is used by Hudi to store all the metadata about your data. This also stores the commits that will be applied to your data set as you apply inserts, updates, and deletes to your data set. Now, going back to our notebook, we can now start reading the data that is written in a Hudi format into a data frame. All right, now that we have read our data, let's take a look at our data and see if there is something odd going on with the star ratings. So we are simply issuing a spark.sql statement to sample a few of our ratings. And as you may notice, there are a bunch of reviews which have a star rating of 100. Now, this is unusual, and so we should be able to update such unusual records and fix them as needed in our database. So to do that, we'll select the rows we want to update and make an update. So in this case, we select all the star reviews that have a rating of 100, and we'll fix them. Now, earlier, if you wanted to update the data in S3, you had to read the old data, merge with the new data, and then overwrite with the old data. Now, with Hudi, you can directly update the data in place. In this case, we have a bunch of records which have a star rating of 100, which we want to null it out. So let's take a look at how that's done. Now we're going to take the records that have a star rating of 100 and fix them with null values. Now that we've updated the records that have a star rating of 100 with null, let's read them into a Hudi view data frame and take a look. As you can see from the output, we had 5 records with a star rating of 100, and all the 5 records have been nulled out. This is what Hudi can do for you. Now, let's suppose you want to delete a customer information for GDPR compliance, or because a request was made by a customer. Now, to accomplish that, all you need to do is read your Hudi data set into a data frame and write it back as an upsert operation, setting the payload class to be an empty record as indicated in this cell. Now, once you do that, that particular customer's information is removed from your data set. All right, now that it's done, let's take a look at whether the delete went through. So to take a look at that, we again repeat the same process. We read the Hudi data set back into a data frame, and we issue a simple Spark SQL statement for the customer ID 320-68341. Now, as you can see from the output, there is no record with the customer ID 320-68341. This implies that that record has been removed from the Hudi dataset. With Hudi, you can also do point-in-time queries. To do that, let's first retrieve all the commits that have happened on our dataset. And to do that, we can issue a Spark SQL statement against some specific tables that Hudi creates, which is the _Hudi commit time table. And once we get the results of the commits, we can issue a sample query against our Hudi dataset that will use the begin time as 0 and the end time as the commit time that we are interested in to retrieve all the reviews that happened during that time, beginning time 0 and the end time as the commit time that we are interested in. And as you can see from this output, this is a list of all the changes that have occurred between commit time 0 and the commit time that we chose from the list that we retrieved. And as you can see, that is the commit where we had removed all the reviews that had a star rating of 100. Now, this simply indicates that with Hudi, you can go back in time and get a snapshot of the data at any point in time. You can also run Hive and Presto queries from your Hue editor or using Presto CLI or even using Beeline from your Amazon EMR cluster. That concludes this demonstration with Hudi. Let's go back to the presentation. All right, let's take a look at some of the infrastructure improvements that we have made on the Amazon EMR service, starting with Spot provisioning. Now, Spot instances are a popular choice on Amazon EMR to run fault-tolerant Spark applications. Now, let's take a look at some of the improvements we have done with respect to Spot provisioning. Now, this graph here shows the percentage of Spot clusters that were terminated globally due to Spot reclaiming the instances every month since 2017. Now, as you can see in the graph, the x-axis represents the timeline since 2017, and the y-axis represents the percentage of Spot instances that were terminated. And as you may have observed, the percentage of instances that were terminated were already low, below 1%. However, we were not satisfied with even that number. And so in 2018, we started an effort to improve the Spot provisioning algorithm to not only look where the capacity is available, but how fast the capacity was getting consumed. And since 2018, if you observe the graph, after these improvements, the percentage of Spot clusters that were terminated has steadily come down. And as of today, the termination percentage remains to be very, very low. Because of the improvements we have made with the Spot interruptions on Amazon EMR, customers can leverage the Spot provisioning to reduce costs with their EMR clusters. They can use the Spot Instance Advisor to select instance types with low interruption rates. You can also right-size your executors to allow EC2 instance type flexibility. You can also use a mix of on-demand and Spot instances for different scenarios, whether you're using a persistent or a transient cluster. And there is also a feature called Amazon Instance Fleet, which will allow you to diversify your portfolio by selecting 5 different instance types, either for your core instance group or for your task instance group. And this increases the resilience of using Spot instances with EMR clusters. Yet another improvement on the infrastructure side that is currently in private beta is managed scaling. EMR customers have been enjoying the auto-scaling feature for a long time. This is the feature where you get to define a set of policies on which your cluster either expands or shrinks. So when using auto-scaling with Amazon EMR clusters, customers define a specific metric, and when that metric exceeds a certain threshold, the cluster automatically expands or shrinks based on that policy. Now, managed policy is slightly different from auto-scaling. With managed scaling, we manage all the configuration, and the users do not have to specify any policies except for the min-max cost constraints. We manage the metrics and decide when the clusters should scale up and scale down. This can save anywhere from 20 to 60% on the cost, depending upon your workload pattern. Let's take a look at the results of a few tests we ran with managed scaling. For these experiments, we used a one-node cluster that scaled as the workload grew. As you can see from the graph, we used an ad hoc workload pattern. This is where we gave the cluster an intense work for 30 minutes, gave it a break, and gave another intense work to do for another few minutes, and so on and so forth. Now, as you can see from the graph, the blue line in the graph represents the load pattern. And the line that is adjacent to the blue line represents when the scale is requested as the workload goes up. Now, you can observe that we almost immediately requested the scale up when your workload expanded. The orange line is where we actually scale up and scale down. From the time we requested the scale up to the time we actually got the nodes and started consuming is approximately 5 minutes. So what this tells you is that managed scaling reacts very well to ad hoc workload patterns. So in this experiment where we started with a one node cluster and expanded or automatically scaled to 20 clusters, we realized 63% savings compared to running a fixed 20 node cluster. Yet another significant feature that EMR introduced is fine-grained access control with integration with AWS Lake Formation. And this is very helpful in a multi-tenant cluster environment that you may have. AWS Lake Formation is a service that lets you build data lakes very easily. One of the primary benefits of using Lake Formation is the ability to centralize your permissioning model. What this means is you can define permissions in Lake Formation, and regardless of what analytic engine you use, whether it's Amazon Athena, Amazon EMR, Redshift, or AWS Glue, those permissions can be enforced in a centralized fashion. So here is the workflow of how Lake Formation works with these services. So a user can set up access in the Lake Formation. This is where they get to define permissions. And when the user tries to access the data using any one of the analytic services mentioned in the box, these services signs the user into the Lake Formation. Lake Formation provides temporary credentials allowing the data access, and user gets to access that data. Lake Formation provides a database-like abstraction via grant and revoke permissions for the users to specify these permissioning. It exposes the concepts of tables and columns on which the permissions can be defined. So on this screenshot, what you see is the tables that are defined in your data lake. And on the right-hand side, what you see is a screenshot where you can specify permissions for users on either the tables or the columns or both for that specific user. So with Lake Formation, you can specify permissions on tables and columns rather than on buckets and objects. While the object level permissions can be quite powerful, they don't work for enforcing column level permissions because all the columns are in the same physical files, even for columnar formats like Parquet and ORC. The integration of Amazon EMR with AWS Lake Formation provides some powerful benefits with respect to authorization. For example, it provides fine-grained column-level access to databases and tables for data sets sitting in your data lake in S3. It allows for shared multi-tenant clusters to access data securely. In addition, it also allows the use of AWS Glue Data Catalog as the metadata store, which can be used by multiple analytic engines. In addition to these, the integration of EMR and Lake Formation has also enabled federated single sign-on from your enterprise identity system. And these include Active Directory Federation Services, Auth0, Okta, and many others. These use security assertion markup language, which is the open industry standard supported by most of the identity providers. This mechanism can also be used as a single sign-on access to your EMR or Apache Zeppelin notebooks. Now let's take a look at what accessing a Zeppelin notebook looks like when it's integrated with SAML and Lake Formation. In this demo, I have a cluster that is configured to use my identity provider, which is Auth0. So when I go to Zeppelin, I'm redirected to authenticate via Auth0. Once I'm authenticated, I'm automatically logged into Zeppelin as my user, which in this case is user Bob. Behind the scenes, we are actually creating this user in the EMR cluster in our key distribution center or the KDC and ensuring that they have a home directory in HDFS. So let's take a look at how this works. So as you can see, I'm directed to the Auth0 authentication mechanism. And once I log in as Bob, I am taken back to my Zeppelin notebook. And here, as the yellow arrow indicates, I'm the user Bob. Now let's start creating a notebook as user Bob. So in this example, I created a notebook called Spark SQL, and user Bob issued a SQL query against a table called Avro decimal. And because Bob has access to all the data or all the columns in Avro underscore decimal table, he's able to see the data in that table. Now, let's switch over to the lake formation console. On this console, I'm showing a database called record underscore server underscore basic, where I have defined several tables. Now, in this example, I'm going to select a table, and I'm going to grant a user named Paul with access to a couple of columns on one of the tables. So as you can see, I'm specifying a user called Paul, who is coming in from my Active Directory, and I am giving this user access to two columns called X and Z, and I'm giving him specifically the select permissions. And I can go and view the permissions and make sure that Paul has access to columns X and Z. Now I go back to my Zeppelin interface, and I'm logged in as user Paul now. Like as user Paul, I create another notebook. And in this example, when user Paul tries to do a select star from record underscore server underscore basic database on the table Avro underscore decimal, you can see that because he has access only to two columns, X and Z, he's able to retrieve those two columns and view the data for those two columns. You can also go back to your application interfaces, and you can take a look at the jobs that were run as user Paul and user Bob, and have a visibility into what jobs were run by what user at what time. So if you look underneath the hood, the query execution looks as follows. The user issues a query in the Zeppelin interface. The query runs on Amazon EMR, and the request for that access to the table is made to Lake Formation. Lake Formation provides some short-term credentials for the table. EMR retrieves the data based on those short-term credentials from the S3 location where the data resides. Now, in order to enable this kind of a mechanism, EMR has introduced a couple of components. One is the proxy agent, and the other are privileged process called secret agent and record server. Now, the proxy agent is responsible for receiving your SAML authenticated request from users. It is based on Apache Knox, and this proxy agent runs on your master node. So it forwards the SAML assertion to Lake Formation. Lake Formation uses that assertion to generate the identity token for the user, which are then stored in the secret agent. And based on the user token, the data is retrieved for that user. Let's take a look at how the query execution works under the hood. So when a query engine requests access to a table, that access request is received by the Amazon EMR record server. Now, this is a privileged process that reads and filters the data on behalf of the query engines. It supports Parquet, ORC, CSV, and JSON, and many other file formats. Think of it as a long-lived JVM process that runs on every node in the cluster. Now, when the record server receives the request, it gets the user token from the secret agent, and then based on that token, it requests access to the table from Lake Formation. And when Lake Formation returns the temporary credentials, it retrieves the raw data based on those credentials from S3. And once it retrieves the data from S3, that data gets filtered by the record server and then sent to the query engine. Today, the supported applications that work with Lake Formation integration with EMR are Spark SQL and Amazon EMR notebooks, as well as Zeppelin with Livy. On the security front, Amazon EMR also introduced the concept of blocking public access to open ports. Block public access is a new account level configuration to help administrators secure their EMR clusters from unrestricted public network access. You can enable this configuration and prevent your account users from launching clusters with security groups that are open ports for inbound traffic from anywhere. You can also configure exceptions in block public access configuration to allow public access on a port or a range of ports before you launch your EMR cluster. On the security side, EMR also introduced the ability to natively encrypt your EBS volumes. Until now, customers used LUKS over EBS volumes to encrypt data. With this addition, customers can now choose either LUKS or native EBS encryption. When you enable native EBS encryption, data on the EBS volumes, including intermediate data, the I/O between the EC2 instances, and the EBS volumes and EBS snapshots are all encrypted. With this, root volumes can also be encrypted without the need to create custom armies. In addition, EBS encryption is transparent to any application running on EMR and does not require you to perform any modification. You can also get simplified auditing by checking the encryption status from the volumes page in EC2 console or through the EC2 API call. Let's switch gears and look at the orchestration mechanisms customers have been using with Amazon EMR. Apache Airflow is a very popular open source orchestration tool that is used to submit jobs to an EMR cluster. Customers typically run self-managed Apache Airflow infrastructure on AWS and submit jobs to the EMR cluster. They have also been using AWS Step Functions to create a state machine that creates clusters as well as runs EMR jobs using the Step API. Late last year, AWS Step Functions integrated with Amazon EMR, making it faster to build and monitor EMR data processing workflows. As you all know, Step Functions allows you to build resilient workflows using AWS services such as Amazon EMR, SageMaker, and Lambda. With AWS Step Functions, you can define your workflows either in JSON or Python, visualize the workflow in the console, and monitor the execution of that workflow via the console. With Amazon EMR and AWS Step Functions, you can now create efficient data processing workflows that order Amazon EMR steps, manage dependencies, and run your work in parallel. You can proactively scale a cluster up and down as part of your extract, transform, and load workflow, right-size the cluster for the task at hand. You can also improve the resilience of your data processing workflow by choosing how the exceptions are handled, such as retrying a failed job and alerting users to failures when they occur. You can also terminate the cluster as part of your workflow when the job is finished. Let's take a look at some of the new capabilities we have added to the EMR notebooks functionality. Most recently, we have added the capability for the managed notebooks to work with Git repositories and also be able to install notebook scope libraries. So as you can see, this is a screenshot of creating a notebook from the EMR console. And as you can see, you can launch these notebooks in either Jupyter Lab or using Jupyter. And you can associate the notebook with the Git repositories where you have your code housed. You can collaborate and share the notebooks, integrate with pipelines, and also have the ability to integrate with AWS Secrets Manager to hold your secrets for your Git credentials. You can now install external Python libraries on EMR clusters at runtime using EMR notebooks. Before this feature was introduced, you had to use a bootstrap action or even use a custom army to install additional libraries that are not packaged with the army before you launch the EMR cluster. With this addition, it allows EMR service now allows you to import your preferred libraries and use them to build your Spark application, analyze data, and visualize results from within your notebook. The notebooks are the notebook scope libraries are only available during the time the notebook is in session, and these get deleted after the session ends. Another feature that Amazon EMR added to help with debugging and troubleshooting is the off-cluster persistent Spark history service. With the one-click access to persistent Spark history server, you can now debug and monitor your Spark jobs by logging directly into the off-cluster persistent Spark history server using the EMR console without having a need to run or perform any SSH tunneling. As you all know, the Spark history server is an extension of the Apache Spark web UI. It presents a visual interface with a lot of information about completed and running Spark jobs on the cluster. You can get job-specific metrics and information about your scheduler stages, tasks, and running executors from the web UI. Amazon EMR now persists this Spark history server along with the event and container logs outside of the cluster and independently of a cluster's lifecycle. What this allows you to do is to access and use the Spark history server even for terminated and long-running clusters alike. In addition to this, you can also access the Spark history server directly from the console, and you no longer have to run through the complex steps to set up and view the web interface using SSH tunneling and setting up the proxy. That's a quick summary of the recent additions made to the Amazon EMR service. To take advantage of these capabilities, go ahead and spin up a cluster with the most recent release of Amazon EMR. If you're looking to migrate your Hadoop clusters to Amazon EMR, we have a detailed migration guide as well as a free on-site 2-day workshop that walks through several stages of this migration program. That concludes this presentation, and we'll open it up for questions now.